this on? Yeah, maybe not. So I'm Todd Woods. I too, continuing the theme, was a student at Colorado when John was there. And just since this is about John, I'd like to tell a quick story that he told at his retirement party, which is, I was only overlapping by 1 year. I took 2 classes from John, the last of which was a reading and research class where John and I met personally one-on-one once a week. And the only thing I can say is after that class, John disappeared. So whether there's a connection or not, I'll let you decide. Little did we know, 8 years later, I'd show back up here. I did have the pleasure of writing one paper with John, which with Richard Klein and Chris McKee on accretion disk winds. And I think it still holds the record as the longest paper in AppJ, is that right? Yeah. Still is, okay. Anyway, our speaker today is Chris Fonts. He's from Los Alamos. He got his PhD from Penn State under Doug Sampson. He has, I guess he got there in '92 as a postdoc and became a staff member in '94. He's developed a set of codes for atomic physics and modeling with other coworkers there. He applies this to a wide range of applications, including ICF at high densities, magnetic fusion at mid densities, and astrophysics at low densities. And his talk today is on a connection between atomic physics and gravitational wave spectroscopy.
Okay, can everyone hear me? Good, yeah? Okay. So as with everyone else, I thank Heather and company for inviting me here. It's an honor to talk on behalf of John or in support of John in his career. I was trying to remember when I met John. I think it was about 12 years ago. It was a virtual meeting. It was via email. And to some extent, I'm John's analog at Los Alamos to the extent that we deal with opacity tables. We both are the people who get the opacity tables out to rad hydro users, so we have that in common. What we don't have in common is our original background. He starts from the rad transport astrophysics application side, and I come more from the fundamental atomic physics side of things. And then a few years ago at Los Alamos, some astrophysicists approached me and said, you know something about opacities, maybe you can help us out. And that's been the beginning of a very interesting rabbit hole journey for me. And I find myself involved in gravitational wave spectroscopy in a distant way, and I find myself reading some of John Castor's 1970s papers. So there are flavors of pieces of this talk that will directly connect to things that you've seen in the last 3 talks. It's a big treat for me to actually hear some of the history because I'm trying to understand not just the physics, but the history and how things connect. So I'll sprinkle in some Castorian stuff in the middle of the talk there. So without further ado, we have entered the age of gravitational wave spectroscopy. Carol mentioned this as one of maybe her last bullet. February 2016, so 18 months ago, the LIGO detector observed a transient gravitational wave. It was predicted by general relativity about 100 years ago, as she mentioned. I love it that everyone's just setting up my talk so I don't have to explain things in much detail. I'll be as fast as possible. And it's attributed to the merger of a pair of black holes. So here's a pictorial. The signal was first seen at the LIGO detector here in Livingston, Louisiana, and then 7 milliseconds later in Hanford, Washington. If you do the math, speed of light takes about 7 milliseconds to go 2,000 miles, so check the box on that. I didn't draw any pictures, but if I could, to scale, you wouldn't see it, but there's an L-shaped interferometer here and one there, and the legs, each leg is 2.5 miles long. And this is quite an amazing device to think about. They're basically doing a Michelson interferometer type measurement where you're shining light down one leg and shining it down another. They hit mirrors on each end and they come back and they interfere. And if there's a little jiggle in either one of those legs or both, you will see a change in the interference pattern. And this is how they're going to detect, this is how they have detected gravitational waves. And they can measure, if you believe it, they say, measure changes on the order of 1,000th of the dimension of a proton. And that's really unbelievable. And they have to, I've seen a few of these talks now, they have to back out the ambient noise of trucks driving by. The vibrations of the trucks will cause these 2.5 mile long legs to vibrate. So it's quite a sophisticated analysis. So here's a chart. I don't know if you can see it all. I boosted it from the internet, so it's in black. I couldn't change the coloring. But the idea is the following. These are different kinds of detectors. And there's LIGO in purple down there. And this is something called the strain, so it's related to how much the legs will move of the interferometer. And the dimensions of the wavelength are the important thing here. This is the range of LIGO, that sort of purplish line, and that's 10 to the 9s, that's 10 to the 6. This is 1,000,000 meters is the wavelength of the gravity waves they're trying to measure. So electromagnetic radiation, which most of us deal with in the room, atomic physics most certainly, is 12 orders of magnitude that way. So we're spanning that way. He's telling me that way. No, that way. No, that way. Smaller wavelengths. It's increasing this way, sorry. Sorry. Okay, I got that one right. That would have been very embarrassing. So 12 orders of magnitude, that way you have your optical and the X-rays and so on. And so the likely candidates for observing gravitational waves are through the merging of two compact objects. And for the purpose of this talk, I'm going to limit compact objects to be black holes or something called neutron stars, which I'll talk about in a little more detail. And as far as the strength of the signal you would get from the merger of these objects, the black hole, which has typically the largest masses, would give the biggest signal. The strength of the signal is related to the mass of the objects, that as they spiral in on each other, they spew out more gravitational energy, and you have a certain strength of signal. And then the next strongest would be black hole and a neutron star, and then finally the pair of neutron stars, which is going to be the bulk of my talk. So here's one of my favorite type of high-level diagrams, just to orient folks. Most stars occur in binaries. Typically, I think it's 70 to 80%. I don't know the exact percentage. But how do these two black holes or black holes and neutron stars, how do they find each other? And before I had achieved this level of understanding, because I'm not an astrophysics person, I thought, because I'm an atomic physicist, you have like an ion and a plasma and an electron, and they find each other and they scatter. Well, the astrophysicist said, no, silly Chris, you don't have a black hole here and one just magically finds the other. They're co-located already. And it's because they originally started as a binary pair as a star, and they undergo their lifetime and they die, and then they're there, and then they can interact again once the process occurs. So you have a binary, and then under the right conditions, you can have gravitational collapse. There are several other paths that a star can take. But in the case of gravitational collapse, you can get a certain kind of supernova, and then you can have either the pair of black holes, black hole and neutron star, or the two neutron stars. And when they merge, they can produce not only gravitational waves, but also in some cases electromagnetic waves. And we've been measuring electromagnetic waves now for centuries. You know, just as Carol mentioned, supernovae were visible to the naked eye. That's hundreds of years ago, around 1000 AD and so on. So we've been doing this kind of stuff for a long time. This we've been only doing for a decade or so. And so here's another chart of the same type of thing, but in a little more detail to show you what's possible. So for the black hole merger, this has the strongest gravitational wave signature, and then medium, and then weak for the neutron star pair. But what about electromagnetic radiation? What are the possibilities? So you have something called a gamma ray burst, in particular short ones, which last on the order of a few seconds. They've been observed. They're likely coming from neutron star mergers, for example, but they only last a few seconds, so you have to be looking in the right part of the sky at just the right time. The black hole merger is not predicted to have a gamma ray burst. So if you want to see both of these in concert, which is one of the goals of astrophysics, if we could see both of these at the same time, that would be, we've already confirmed that it's a gravitational wave observation, but to tie the two different types of physics together would make us feel a lot better. What about something called a light curve, or more raw electromagnetic radiation that lasts on the order of days, something that you have a chance of seeing? Well, the theory again says no chance for the black hole merger. It's so dense that the light never escapes, the Schwarzschild radius, that kind of thing. But for these two, when you have a neutron star involved, you can get electromagnetic radiation. And the question is, what would it be? So that's the subject of this talk. And when these merge together, they're called sometimes a kilonova or a macronova. Kilonova because the intensity of the light that comes out is predicted to be roughly 1,000 times a regular nova. Since then, so I would say the research for this type of light is about 20 years old, give or take, and it started off as 1,000 times a nova, and it keeps getting less and less and less. So less optimism about being able to see the electromagnetic signature in this case. So I didn't coin the phrase, but I'm trying to push the phrase macronova, just bigger than a nova, but we don't really know how much. So can we see the electromagnetic radiation in coincidence with gravitational waves or not? And if so, what will it take to see them? So another picture of a neutron-star merger. Again, the star has died, and it leaves these two objects here, and they are spiraling inward on each other. There's a well-defined axis of rotation. There's an angle of inclination with respect to the Earth. So if the smiley face represents us on Earth and we have a telescope looking, there's going to be an angle relative to the plane of the object. And that's important. And so there's a curtain of ejecta. As these two spiral in, they start the radiation and such and momentum starts pushing out this ejecta. It is made of highly exotic elements compared to most things in the sky, compared to, I'll say, regular stars. While regular stars may have trace amounts of these, here's the heavy elements, lanthanides and actinides, regular stars may have trace amounts. These neutron star mergers are predicted to have relatively large abundances of these elements. So if you're a visual person for the periodic table, it's these two rows down here that if you've never looked at before, and I know many of you have looked at these before. You've got uranium and plutonium, for example, down here. But these are the ones that are these nasty so-called F-block elements where you have electrons in the F shell, and they're very difficult to calculate, et cetera, et cetera. So in a little more detail, 3 types of emission: gravitational waves. I used to say it was never observed so far when I gave this talk before the observation was announced. It has been. Almost certainly will result in a Nobel Prize. The gamma ray bursts are less than 2 seconds long. They're created by the rapid capture of neutrons, the so-called R process. There's also an S process for slow neutron capture. But the chances of seeing this are low, not only because the time duration is small, but because the gamma ray bursts are directional. They come out typically within a narrow cone about the axis. And so you'd have to have the merger tilted towards the Earth, and you'd have to be looking at just the right time. So not a huge chance of seeing a gravitational wave in concert with a gamma ray burst, although it's possible. Anyway, from the radioactive elements that are involved here, and by the way, you have to have neutrons. These are neutron stars, so their atmospheres are rich in neutrons. You have to have neutrons in order to get our process to go. They get heated, create the gamma ray burst, but also from the radioactive decay, the ones that are trapped inside of this ejecta get down scattered to lower and lower energies and say, I want to get out, I want to get out. But at what frequency will they get out? And at what intensity will they get out? And can we measure them? And the lingo that the astrophysicists use, it would be a light curve in this case, and the opacity is what decides what gets out of the merger. So another one of these high-level diagrams, the top part is the same piece as before. What's a light curve, if you don't know? Well, once the star goes supernova, it's going to emit a light depending on its type over a certain amount of time. And here's a generic diagram of various types of supernovae. They have exotic names like 1A and 2P and so on, and they have this basic shape. They peak on the order of, after the explosion, on the order of tens of days. And so those you can see in the sky with the naked eye, and you can certainly see them with telescopes, and we're seeing a lot more of them now. If one telescope sees them, it talks to the others around the planet, and they all point, and we get a lot more data, to the point where now we need people to mine the data to see if there are any trends. But the basic idea is this is the generic shape of a supernova light curve. What about a macronova? There are lots of guesses. There are maybe even 2 or 3 claims that we've seen them, but they don't really fit the theory based on what I'm about to show you. So are they similar, or are they different to supernovae? Before I go into some additional details, I want to just say another reason to study neutron star mergers is we don't know where the neutron-rich superheavy elements are formed. We can only describe about half of their abundance in the universe so far. caused by supernovae. So in this diagram, which again I lifted off the internet, you can see that supernovae are responsible for a lot down here, but only about half of their abundances can be explained. So one of the lessons is don't believe everything that you read on the internet, because that's been an outstanding mystery. I think almost every year for the past 10 years, it's on the top 10 list of unresolved mysteries we can't explain. And so if you remember your nuclear physics, when you have the rapid process, the R process, you're basically going to stair-step through this valley of stability and work your way up, and you change one element from a certain Z and capture a neutron to Z plus 1. So you get to heavier and heavier elements. And so this is a plausible explanation for how to get the super heavy elements, super neutron-rich heavy elements. Okay, so let's go back to the neutron star mergers now. The initial conditions, when they first meet up, are temperatures on the order of 1 million electron volts and very high densities, 10 to the 14. And then as this ejecta starts expanding, it becomes much more rarefied. The density drops quite a bit, and the temperature also drops quite a bit. So now you're on the order of 1 eV. So when, I don't know about you, but when I hear 1 electron volt, I think that's relatively cold. The matter is going to be roughly, because of these densities also, very low densities, it's going to be roughly neutral, which means the bound electrons are going to be present. They're not going to be ionized. So from an atomic physics point of view, you have 50 or more bound electrons, and that's a crazy calculation. It certainly can be done. We have codes that can do that, but to do it in detail for this type of calculation is not straightforward. And if you told me 25 years ago when I finished my PhD that I was going to be calculating cold lanthanide and actinide opacities, I would have said that's crazy. But things progress, not only in the observational realm where we can see gravitational waves, but also computationally and theoretically. And so as an example, I'm just going to pick samarium, Z equals 62. I could have chosen any other, but I just chose samarium. And we're going to have because of the temperature is cold, we only need to deal with the first 4 ion stages. So neutral, once ionized, twice ionized, and thrice ionized. All the others have a very low abundance for these conditions. And here's the standard ionization balance curve. The neutral dominates at the lowest temperature, and then it drops down, and then once ionized, twice ionized, and so on. This is the LTE answer. And by the way, everything I show here will be LTE. That's a favorite assumption of atomic physicists and astrophysicists because it's easy. The standard disclaimer applies. It may not be right, but we have to start somewhere. Okay, another simple concept. This was the earliest attempt 15 to 20 years ago to figure out what is the opacity in the ejecta. And the idea is, this might be a bit sarcastic, but astrophysicists are famous for their back-of-the-envelope type calculations. And they say, let's assume all the free electrons are the only thing that causes the opacity. So we'll do Compton scattering, even though we know there are many bound electrons, and we've heard many talks about how the lines are important. I'm getting there. I'm almost there. But if I just assume Thomson scattering is that simple formula, 0.4 times the mean charge divided by the atomic weight. And for these 3 temperatures, I've listed the mean charge. So once ionized, twice ionized, and thrice ionized in the neighborhood of 1 eV. And they give these boring flat curves for the opacity. So this is the probability of absorbing a photon for any frequency. Boring, boring, boring. It means if a photon is trying to escape through the ejecta, it's going to have roughly the same probability no matter what. And so if we can see one photon energy, we should be able to see the others equally well. Well, we know that there are many bound electrons, and so I did just a simple calculation of putting in 25 configurations spread across these 4 different ion stages. And this is relatively simple to write down, and you realize it grows very quickly to a large number of energy levels, a large number of radiative transitions, and again, this is beyond anything that I had imagined calculating 25 years ago. So when you do that, instead of the flat curves, which are holding up the opacity, now you get this massive set of lines. And this is what Stan was referring to if you were listening to his talk. He said the scattering cross-section is down here, and the lines are, what's that, about 10 orders of magnitude, 8 to 10 orders of magnitude higher. So now suddenly it becomes almost impossible for photons to escape here. They try to escape, they get absorbed by a line, and the line says, I'm going to re-emit you, and there's going to be another line there, and so on. And they're just not going to get any chance or have a very low probability of getting out in this forest of lines. And this is the optical window, so this is visible photons. There's a few EV. They have almost no chance of escaping. So I think somebody did report an optical observation 3 to 5 years ago, and that's not likely based on this set of calculations, and there are even other calculations from a Berkeley group that precede this that say the same kind of thing. The chances of getting out in the optical are very slim. So what will we see? And what does this have to do with John Castor? Well, one more picture. This is dysprosium, Z equals 66, just 3 elements away. Same pattern. And this happens for all the lanthanides and all the actinides, over and over again. So, how do you combine all of those lines in some manner to get a reasonable radiation transport calculation out? There's no way that you can build a computer that can track every line at atomic resolution and get all the absorptions and emission on an atomic time scale. And you'll probably see where this is going. You've heard multiple talks about John's work in the 70s and how you can get clever and use all these lines in a particular way. The natural broadening just from quantum mechanics is very narrow for a line in general. You typically can't resolve that kind of thing, especially for a lanthanide, unless you had a very fine photon energy grid. Doppler broadening is not very large as well because the temperature is so low and the mass is so high. So I'm not going to get much luck there in terms of broadening, having the lines be broad and being able to resolve them. And as you know, to get a bound-bound opacity, you sum up all the lines. That's the oscillator strength. You have their populations, which again I'm assuming is L to E. And you have a line shape, and you plug these widths in, and you get a bunch of sticks, basically, like I just showed before. But nature is somewhat kind in this case, and this is some of the work that John was doing in the 1970s. If you have an expanding medium, then when you have well-defined lines, you go from this picture where a photon hits a line, comes out and sees another one, to something like this, a quasi-continuum. And so you have basically, because of the expansion, you have a redshift, and the photon gets redshifted continuously and hits the line many, many times, or sees a blanket of lines, and it can't escape easily through that forest. So here's the connection with John, a condensed historical timeline. I could have put many other authors here, but just to put John in context, there's something called the Leningrad School in Russia, 40s, 50s, and up to the 60s, with a gentleman named Sobolev, whose name you've heard. And I don't know if this is true, but as far as I could tell, John is one of, if not the first people in the West to actually take this approach and apply it. David Hummer was translating Ivanov's book around this time. But it seemed like John was one of the people to pick the ball up and running and develop it further and apply it to problems in the West.
Harvard people who were following Sobolev very early on.
Okay.
But they didn't produce a lot of work.
Okay, we can discuss that. I'm very interested to know the history. You can tell me more. So John's applications, as we heard, were stellar atmospheres and winds. Then we have Karp et al. In the 70s wanting to study supernova light curves. Pinto and Eastman also doing some more theoretical and numerical work. And then in the present, we're now working on these neutron star mergers. And it's interesting that as you move down this chart here, it's also a map of complexity of elements. Meaning up here, you're typically dealing with hydrogen-helium type light elements. And then in the supernovae, you're getting into iron peak elements, so iron, chromium, nickel, et cetera. And then now we're dealing with the crazy lanthanides and actinides. So as the astrophysics considers more complex objects from a spectrum point of view, we're also getting involved in more complex atoms, and the atomic physics is keeping up. I wouldn't say this is driving the atomic physics, but it's certainly, they're moving in parallel. So we've heard about the 1975 paper in particular. There are 2 papers that precede it that I just wanted to underscore a little bit. The 1970 paper, I think one of John's first 5 papers that I've been trying to understand as an atomic physicist. And again, I just want to point out, you see escape probability method and the transfer of lines. So this is the business of the radiation really is going to act strongly with the lines. And I think I had to cut and paste this. This is back in the day when you see the author's name up front, and then you have to go to the end of the article to see where are they from. And sure enough, he was at Jill at this point in his career. And then there's the 1974 paper also, which Stan, I think, put up in the highly cited lists, or maybe it was 1971. But again, body force on the material, and you have line emission, same kind of pattern. And these papers are all about taking this large list of lines at the time and trying to put them in a code and get something reasonable out. And finally, I wanted to point out, he gives props to David Hummer, who was doing the translation of Ivanov's monograph. We've heard about, we know that John is quite intelligent. He's not infallible, though. I am grateful to the referee for pointing out a flaw in the Voigt profile. Thank you very much. So he's also very humble, as we've heard. So we have a new method that we're proposing, somewhat controversial. The Sobolev method is the one that I just described, where you can take the lines and sum them in bins. The method that we're proponents of is a line smearing that preserves the area under the opacity curve. And that will give a much higher opacity. And instead of using this slick formula, we're doing a much more computationally intensive one where we have to smear each line out. And we're not sure if this is the best option, but since neutron star mergers haven't been seen in the predicted bands using this approach, we wanted something that would increase the opacities more. And that's why we are using this particular approach. And when you do that, I'm not going to go into too much detail, you get the black line as opposed to the green line. And the black line is smeared, and it makes sense up here. You say, yeah, the black line is more averaged than these sticks that weren't smeared out, so it kind of goes in the middle. Over here, it doesn't go through the middle, and you look and say, what's going on there? Well, it turns out the lines are so narrow in the green curve, they would be very tall but very narrow. I couldn't even resolve them. So this method has an added benefit of smearing the lines to the point where you can resolve them on a grid and put them in a code. Here's a plot that shows the difference between the Sobolev method, the traditional method down here for z equals 60, and an order of magnitude increase using our approach. Again, controversial. Astrophysicists are discussing this right now. And here's closing on the end. Here's essentially the light curve, the log of the luminosity as a function of time, just like I showed you for supernovae. Now I'm showing it for neutron star merger for different masses, so 1.4 solar mass, 1.4 solar mass, et cetera, and using a non-relativistic model and a relativistic model. And so there are 6 curves up here that correspond to the infrared band. There are 6 curves here, 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 and here that correspond to the near infrared band. And then there are 6 curves here in the optical, which are so compressed that you can't even see them. So this is what you get when you use these opacities. And here's the takeaway. The optical band you will have almost no chance of seeing, not only because the opacity is so high, but the duration of the light that comes out is so short. You'd have to be super lucky to see that. The near infrared, which is next down in energy from the optical, has a much longer duration. You're on the order of tens of days, so that's good news. But its luminosity is still, this is decades here, 1 to several orders of magnitude lower depending on which model you use as a relativistic and a non-relativistic one. There's quite a spread. But they're lower compared to the infrared band. And so our predictions say that most likely, if you believe our approach, we should be looking at an infrared band. The bad news is we have, or I'm told that, as you move from this band to this band to this band, you need to build an instrument that will measure them. It's an order of magnitude in money to go from here to here and from here to here. So the observers don't like that very much. But that's where this particular theory has led us. So again, most intense and longest duration wins the day in this kind of thing. So in summary, I've talked about lanthanide and actinide opacities that I thought I'd never be calculating. John was involved in the expanding the original Sobolev method. We've proposed an alternative approach. And the accurate characterization of the radiation is going to be playing a role in continued discussions of how to find this particular radiation. Thank you.
2 minutes for questions. Anybody? John?
Let me put in another plug.
Wait.
Let me put in another plug for the paper with David Friend, the
Okay.
multi-line scattering
Okay.
paper, because I think that would work just dandy for your problem,
Okay.
and it should also conserve the integral over the opacity that
nice.
you were talking about. So, unless I'm mistaken, but
Yeah.
maybe we can talk, you know, it's a simple formula. I'll be interested to see what happens if you apply that formula.
Yep.
In the neutron star mergers, how certain are the kind of initial conditions? Do they depend on the nuclear equation of state or any of the high density
Yeah,
physics?
so they call that morphology in their business. It's very compartmentalized. This astrophysicist does this and hands it off to the next one. I'm not a super expert, but I think there's a fair bit of uncertainty in those conditions. I've seen multiple papers of just the composition, the abundances are not certain by order of magnitude or more. It's related to the cross sections.
Okay, we have time for one more.
Heavy elements, the lanthanides and so on, are neutrons that are getting sloughed off, presumably. So there's going to be a huge beta decay chain. Is there a chance of seeing neutrinos from any of these?
That's a good question. I've never considered it myself. I've never heard it in astrophysics context, but I will try to find out.
Okay, thank you.
Thank you.